Good afternoon. My name is ilya.nazarenko. I'm technical solution consultant with Siemens. Today I'm going to present you with a solid edge simulation solution, which is part of Siemens solid edge portfolio. We're going to take a look at challenges that exist in the industry related to FEA analysis. We're going to take a look at Siemens solid edge portfolio. We're going to talk about solid edge simulation capabilities. And finally, we're going to take a look at solid edge simulation in action. So we're going to actually look at live content, and we're going to see how solid edge simulation addresses different challenges. So what are the issues facing design engineers today? The job that today's engineers are faced with has to cover a multitude of different tasks in all phases of product development. It includes analysis, it involves use of several products, each with its own interface and method of working. Often, tasks like simulation are outsourced, which separating analysis from a design process. This reduces the number of analyses that can be performed, and it prevents analysis from being used for investigative studies, which overall inhibits innovation in the design area. Some of the solutions available today are either overly simplistic in their approach, which of course can compromise solution accuracy and create misleading results. Some of them provide no ability to edit geometry easy after analysis is done. So, which means there is a lack of associativity between the original model and the FEA solution. Solid edge simulation addresses all these challenges successfully because it's a one single integrated environment with a simulation tool. It's using the same underlying geometry and user interface as solid edge applications. Another point I'd like to make is that solid edge simulation is easy enough for any solid edge user to master. Of course, the person who needs to address FEA analysis needs to be familiar with principles of the analysis, but the solution is robust enough to service most of engineers' analysis needs. By enabling engineers to perform their own simulation, more analysis gets done in less time. It improves quality, it reduces material costs, and minimizes the need for physical prototypes, which is a big drain on the financial system of any company. The layout of the user interface is designed to guide the user through the whole analysis process, which makes it easy to learn initially and revisit if necessary. Let's take a look at solid edge simulation capabilities. First of all, solid edge simulation provides both automatic and manual methods of mesh creation. It provides also precise local mesh control for higher accuracy, specifically around stress concentrators. Full complement of loads and constraints is available for defining realistic operating environments because our goal is to mimic the real world situations as close as possible. The underlying solver technology is an Nestron. It's de facto industry standard solver for finite element analysis. It's industry proven technology. Variety of analysis can be performed, including static, normal mode, frequency response, buckling, heat transfer, harmonic response, and so on. Users can interpret and understand the result in model behavior quickly with a comprehensive graphical post-processing tool. Circus technology, on the other hand, allows for history-free model changes at will, which drastically speeds up the model refinement process. When we talk about solid edge portfolio, by looking at this slide, you can see that it depicts the whole depth and breadth of a current solid edge portfolio. With key solutions in mechanical, electrical design, simulation, manufacturing, tech pubs, data management, and cloud-based collaboration, solid edge portfolio enables digital transformation for companies of all shapes and sizes, helping speed time to market and lead in their respective markets in ever-changing environment. Note that solid edge simulation goes into the third column, specifically dedicated to FEA products that are part of solid edge portfolio. Siemens recognizes the importance of delivering highly capable analysis tool to the customer base. Finally, we can take a look at the product, and we're going to focus on three different cases. First of all, we're going to see how successful solid edge simulation in analyzing thin wall model types, because it's a very important topic. A lot of companies produce sheet metal structures and sheet metal designs, and they need to catch mistakes related to structural integrity early in the design cycle. We're going to take a look at frame structure analysis, specific type of mesh beam. It significantly reduces processing time, it delivers results quickly, and results are accurate. And finally, we're going to take a look at how we can utilize feedback from another solid edge environment, motion. How can we find the reaction forces and use them in solid edge simulation as loads? So all these three cases we're going to explore right now. Solid edge simulation is a tightly integrated solution within solid edge, and it equally well performs whether we analyze in solid bodies or thin wall components, like in this case sheet metal parts. Many companies design in sheet metal structures, and some of them quite complex, and they need a really reliable tool that would allow them to analyze sheet metal parts. As I mentioned, this requires a special type of mesh shell element, and we're gonna focus in this segment on this particular task at hand. So what we're looking at supporting structure for lawnmower. As you can see, the seat transfers load through this plate and via the springs onto the lower structure, and we need to evaluate whether this supporting structure is capable of supporting the specific weight. So let's isolate components on the screen that would be focused on. We can easily accomplish that with display configurations, as you know. So first thing we're going to do, we're going to extract mid surfaces. And for that, solid edge is a very efficient tool because you don't have to dive into the part. You can extract mid surface directly on assembly level. With one single click, we can go and extract every component's mid surface, and we're pretty much done. So now if we hide all these three components, we're left with structure of extracted mid surfaces. And now we're ready to dive into simulation. Simulation is, as I mentioned, very tightly integrated within solid edge, and we can create new study right here, or we can go and open the sidebar. Tool is very flexible. You can progress from left to right in this situation, or we can go from top to the bottom. So I can create new study, and in this case, I'm going after a specific type of mesh, surface mesh. And we're doing linear static on these three pieces. We can conveniently select all of them at once. It doesn't require you to pick one by one. Before we actually start applying loads, I would like to point out that we're interested in the specific areas around these holes. Remember, those springs actually have a limited diameter. So what we can do, we can conveniently use this offset edge, and in one single operation, we can offset all three edges. And solid edge not only offset them, it actually splits our surface into specific areas that we can conveniently use to apply that particular load. And then we can just go and apply constraints and loads. We have all kind of type of constraints, fixed, pin, no rotation. In this case, we're gonna go with fixed. And again, it's very flexible. It allows you to select edges, points, even features. So in this case, we're interested in the bottom couple edges right here. And as far as loads, again, we have all kind of loads available. We're talking about force, pressure, torque, displacement, bearing, hydrostatic pressure. In this case, I'm interested in the force. And of course, very efficiently, we can select all three faces at once and define maybe 300 pounds would be sufficient for this type of load. Now, since we're dealing with assembly, solid simulation needs to know how these components interact with each other. So we can easily identify minimum distance, let's say, between these two elements. And we've seen that it's about 0.17 of an inch. So when we define our surge tolerance, when we create connectors, and we can do so automatically, very conveniently, we can apply surge tolerance slightly larger, let's say zero point 0.2, than that value we just measured, and then we can just select all components, and you can see Saudage simulation quickly and efficiently finds specific connectors for this geometry on screen. Very visual way of looking at these connectors is available right now in SouthEdge. So we can quickly toggle on and off adjacent geometry of the rest of the assembly, so we can see where exactly in assembly we are at the moment. If we're dealing with a complex structure, we can take a look at both target and source faces, or we can isolate only specific target or source face. And we can delete specific connectors if we're not interested. But in this case, I'm going to create those default connectors, and we're pretty much done. What's left to do is just mesh and solve. Because it's simple enough structure, we can just mesh and solve in one single operation. But before I do that, I'd like to point out that I can actually go and change what we call subjective mesh, which allow us to control how fine we want that mesh applied to the whole structure at this particular point. So we can click mesh and solve, and SolidEdge will go to work. It will take all the boundary conditions, load into an Nestron, and in a second it brings back the results and opens post-processing window. We can easily identify what's happening, and we can interrogate our structure. So if we can conveniently animate the structure and see how it performs under this particular load, and we can see that stress is about 14 ksi. We would like to probably lower that particular stress. So in order for us to do that, let's go and get out of that environment, and conveniently we can go through multiple iterations, and in this case I can do it manually. Let's say I take this static study, just drag and drop on simulation tab, and will create exact copy of previous study with all the boundary conditions, loads, and all the parameters applied. So what we're going to do next, we're going to add additional components. And the same way like I did before, I can extract mid surfaces in no time from this extra supporting structure. Remember, we need to reinforce this structure. And as you can see, when we hide these components, original components, we see the extra couple elements are added, or I should say mid surfaces added to our structure. And nothing goes to waste. The system is very efficient. So I don't have to go and start from scratch. In this case, I'm going to go and define geometry and just add those couple extra pieces. As far as material thickness and material itself, SolidEdge simulation is so efficient, and because it's tightly integrated within SolidEdge, it can extract all this information from assembly design. So it knows all about material, it knows all about thickness of the part. So in this case, all the loads are the same, but as far as constraints, we can go and easily identify this constraint and add to it. So as I said, we don't have, nothing goes to waste. We don't have to start from scratch. We could just add couple faces to our constraint. As far as connectors, we can do again automatic connectors and select defining the right tolerance. We already know what tolerance, surge tolerance is. We can select only specific parts. We don't have to go and redefine all connectors again. So it finds the connecting elements on those extra elements we just added. And all left to do that is just solve this. When we solve, you have to realize that SolidEdge simulation, because it's tightly integrated, it knows all about boundary conditions, all about mesh, so we don't have to redefine all those. It all happens automatically for you. This is how system delivers very efficient approach to simulation. Let's go and animate this result. We can see that now supporting structure reduced stress drastically. It's probably half of the original stress. Now it's only 6. And by the way, we can easily look at results of a previous study just by clicking at results of the first study, and you can see it's a 14.7 KSI, and the results for the supported structure is only 6. So we achieved our goal. We reinforce the structure. And of course, all this information may be needed for design review or for future reference. We can conveniently create with single click, we can create report, and that report would be in the HTML base format or Microsoft Word. And with a single button click, Solid Edge simulation will capture all the information in a very nice template-based report where table of contents is available. We can take a look at loads. We can create all the information that pertains to this particular study. We can take a look at particular images of this study. And this is really great way to capture all this information and store it somewhere for future consumption, whether it's for design review or for sharing with your customers, vendors, and so on. So you could see how Solid Edge simulation is very efficient at analyzing thin wall structures because of the 2D shell element available, which delivers accurate results and significantly reduces processing time. Let's take a look at analysis where frame structures are involved. Solid Edge provides really accurate and very fast solution utilizing beam type of mesh. So we're going to be analyzing this engine hoist assembly, which supports 2.5 tons. As you can see on the screen, we have many elements here, and the whole thing was designed pretty much using frames. As usually, we can isolate components on the screen really fast with the assembly configuration. And then we can just simply dive into frame environment because this is where this type of analysis is available. And immediately when we start simulation, you'll see that only type of mesh beam is available in this particular case. We can say select all the components, and at one single click, system will create the linear element representing those beams. One thing I'd like to point out that it connects elements with what we call rigid links. And this is a very powerful way of connecting elements and quickly getting results. Not only we can do it automatically, but I'll show you later how we can do it manually, and it will improve productivity drastically. So in this case, I automatically connected and extracted all the beam elements. And what's left to do is to define the constraints. And as I mentioned earlier, constraints are quite flexible, so we can define them apply to curve, or in this case, we're going to apply them to nodes. And we're going to apply them at the points where supporting structure exists. In this case, we're talking about these casters. So we define constraints at every point where supporting structure is. And as far as loads, as I mentioned, it's a 2.5 ton hoist. So we can define the load as 20,000 newtons. That's roughly 2.5 tons. Okay, now that we assign all this, you can see it takes no time at all. All we have to do just mesh and solve. And keep in mind that because we're using this type of mesh, the results come in really quick. And as you can see, we are slightly exceeding our yield stress. Yield stress for this material is 380. We're at 433 megapascals. So let's animate our results. And I usually tell customers that if you look at the structure in the post-processing window, it's very beneficial to take a look at how it animates under this stress. And if we take a close look, you can see that pretty much these two elements, they're not working at all. So they're not even attached to the vertical member, and they're not doing their job. So let's take a look and go back into our study setup. environment. And let's take a look. First of all, you'll notice that these two elements interconnected with this rigid link, but they're not connected to the vertical member. And the reason why, because solid simulation has a tolerance that is set up for study when you create that study. If you go to modify the study and take a look at options, this tolerance is available at the time when you create study. What happens if you didn't do that? So apparently this 89 millimeters default tolerance that was saved within the system is not enough to automatically connect those elements. So what do? We again, when you create study for the first time, you can define it here, or in this case, I can add them manually. So I can say, let's go and create manual rigid links. And now system gives us chance to define that tolerance, but let's keep it the same for now. Because even with this tolerance, I can still go and manually define these rigid links. So first of all, we select elements that we want to connect and select points on those elements. And system conveniently creates this rigid link for us. Same thing on the other side. But when we take a close look at the situation, you can see that they're not completely aligned. They're close, but not completely aligned. So let me outline what I mean. So in this, if you take a look at this area, you can see that they're not coincident, those ends. So let's go back. We can undo a couple times. And instead of doing it manually, we can the same way apply automatic rigid link. Define, let's say, bigger tolerance. And then conveniently, we don't have, imagine you have more complex structure. You don't have to manually go and select. You can still say, select all the components, and system will automatically figure out which links are not created based on new tolerance. As you can see, it connects only, it keeps all the previous rigid links intact, and it connects and creates only new rigid link. Not only created perfectly, but also it coincides with the plane if you create through to back supporting elements. Okay, now that we added that connector, we can solve it again. And as results pop into post-processing window, now we can see that we lowered stress significantly. Now we're very close. We're even lower than 380. We're at 373. Again, let's animate our design, post-processing results. And now you can see that those two elements in the back, they are working, they're doing their job. So they support the structure. But if we take a close look at this situation, apparently it's not what happens in the real world. Remember, what we're doing, we're creating digital twin, which means we have to mimic real world situation as close as possible to get accurate results. And in the real world, that smaller cross-section beam would not be protruding through a bigger size beam. So what do? We handle this with manual connectors. As I said, the system is very flexible and yet very powerful. So we're going to go and create manual rigid links, and we can connect these two elements properly. So we're going to connect this element at this point with this element, let's say, at this point. So we created this additional link here, and we create additional link at this location where the smaller cross-section element comes out of the larger section. So again, we select this element, and then we select the lone element. And we connect second rigid link right there. So now keep in mind that I'm not doing anything with loads, with boundary conditions, with mesh. Everything's pretty much handled automatically. So this allows you to go through multiple iterations in no time and fine-tune your study and your boundary conditions as you desire. So now if we animate our design, you can see that system performs as it's supposed to. And if we take a look at stress, you can see that we're at 250, which is much lower than 380. So this is how this type of analysis delivers really fast results but accurate results. And you can fine-tune your design as you wish using this type of approach. So let's go and take a look at the other area of this hoist. Let's get out of the frame environment, and this time we're going to focus on the area where actually the engine would be mounted to. Let's see how well it will withstand the load of 2.5 tons. The advantage that I'm trying to show you here is that Solid Edge can handle multiple type of studies on the same assembly. So before we dive in, first of all, I'm going to extract a couple mid surfaces, since these side plates are sheet metal parts. I can easily take advantage of that. And then after we extract it, all we have to do is just hide all the elements that we don't want to see, and we're ready to start our study. This time I'm going to select mixed and general bodies type of study. The reason why I'm doing that, because we're going to have mix of solid bodies and sheet metal structures. So I'm going to select, of course, these two elements that we extracted. I'm going to select this particular beam, and I'm going to select the structure that supports that beam from the bottom. That's all we need for our study. Let me explain a little bit what's happening here. So if I go and section this assembly, you can see that inside we have this threaded rod, and this threaded rod can bend because of its length. If we exceed certain load, it will start bending significantly, and that will prevent that centerpiece, which is supposed to move along that threaded rod. So we need to prevent that. And in order to do that, we need to make sure that certain displacement of that rod is controlled very tightly. So let's go and do that. So we have the geometry. All we have to do is just add the loads. And as I said before, Solid Edge simulation is very flexible. We can select faces, edges, points. In this case, we're going to select a couple edges, and it's going to be the same type of load we used before, 20,000 newtons. Now, as far as connectors, remember, we're dealing with assembly, so we can go and create connectors. Easily, system can handle this. And Solid Edge simulation will go and find all these connectors for us. And as before, we can conveniently turn on, turn off surrounding components that are represented as translucent geometry, so we can easily see where we are in assembly structure, and we can take a look at both or single target and source elements. So in this case, I'm going to accept all 8 connectors that were created, and we're good to go. Of course, we need to add constraints, and then add constraints, we're going to add constraints to this feature. Conveniently, we can select all the faces of that structure that supports beam, and all that is left to do is go and mesh and solve. The results will be quickly delivered in the post-processing window, and of course the results are going to be exaggerated. That's a good thing because you can see how they actually perform under this stress. And if we take a look at displacement, this is the one we're interested in, not only stress, but mostly displacement. And we can take a look at actual displacement, not exaggerated type. So when we go and animate, you can see that that rod is moving quite a lot. It's about 7 millimeters. This is not acceptable because it will bend, and we're going to have a bad situation with our design. So what we can do, we can adjust the length of the beam, and we can adjust maybe thickness. Because we're working with synchronous technology, we can do that right from the top level of assembly. So we can select this element, and we can define the overall length as, let's say, 600 millimeters. And the rest will get updated. And while we're at it, we can select the dimension for the thickness and change it also, let's say, to 3 millimeters. And we could go and solve it again, but we don't want to go through all these iterations manually. That's why solid edge simulation provides a way to automate this process, what we call optimization. I can right click on this study and say create new optimization, and going through a couple screens, I can define different parameters. So what are we looking for? So we're looking for total translation, which would be in a specific range. So we can define it as a minimum, maximum, or target. In this case, we're interested for 1 millimeter displacement or translation. Then we can conveniently add limits. What are we going to limit? We're going to limit stress. Let's say I want to stay within specific stress value below, let's say, 190 megapascals. And finally, what parameters are we going to be modifying to achieve that? Conveniently, we can get access to components, not only top-level assembly, and we can get variables from there. We can utilize multiple variables if we want to. So as we add those, you can see solid simulation extracts automatically even the range of motion for those variables. And finally, we can define number of iterations and go into optimize. You can imagine how much time you will save by doing that. If we watch closely, you can see that length of that element would be changing and thickness of that beam is going to be changing. System will go through 6 iterations and will find the most optimum solution for you while you're having a cup of coffee. Think about efficiency. Think about save time and avoided liability issues if that hoist fails for any reason. So after the system is done processing, it will give us chance to look at the results and pick the most optimum result, of course, for this particular configuration. So we take advantage of Microsoft Excel when we view a summary, take a look at the results, and evaluate results. And as you can see, probably the latest iteration is the best one. We are below 190 with stress, and we're almost exactly at 1 millimeters. So the thickness is about 5.76 of a millimeter, and the length would be 740. So I would say the stock doesn't come in this number. So we want to go maybe with the 750, the length, or 740, and the 6 millimeter thickness would suffice. So all we have to do is just, first of all, we can take a look at the graph as well, see how iterations, all the iterations were displayed during the analysis. You can save this spreadsheet if you want for future references. And all we have to do is, again, go back to our design and change this to maybe 740 and 6 millimeters thickness. And if we solve this study, we'll get our results that we were striving for. So we can see the stress is 161, and if we take a look at displacement, it's below 1 millimeter, 0.954. So you could see how solid edge simulation, being tightly integrated within solid edge, allows you to quickly and efficiently analyze the same assembly for different types of analysis and arrive at the proper solution to avoid any liability issues down the road. We were able to analyze the hoist structure built out of frames and use beam type of mesh. And also we were able to automate the process of optimization of your design. While you're having a cup of coffee, system arrived for you at the most optimum result, meeting your requirements. Let's take a look at this example of crankshaft analysis. We're going to explore how solid edge motion enhances results of this particular study and how it contributes to more accurate, more realistic results delivered within solid edge simulation. So as you can see, we have a single piston mechanism here. And before I dive into motion, I would like to set up a study. As you know, in SolidEdge, with the SolidEdge simulation tightly integrated, it's quite easy. We can just go and select Create New Study. And we're going to focus only on this crankshaft. That's the one we're interested in. As a matter of fact, let's go and isolate this in the screen. As far as the loads, we're not going to apply any loads in this case because, again, as I mentioned earlier, we're going to use SolidEdge Motion to extract this information from motion analysis. But we're going to constrain this model on both sides. And we're pretty much done. So now at this point, I'm going to go and dive into motion environment. And again, motion environment and very tightly integrated within SolidEdge. As you can see, it's one of the environments in assembly mode, and we can create new mechanism. And when we do that, motion will automatically place components in appropriate groups. As you can see, if I accept, you can check and uncheck any particular component if you want to exclude from automated workflow, but I'm okay with that. And sure enough, it does this really nice job of placing components in appropriate groups. So all these are moving parts, and the engine block is segment, I should say, of engine block is a stationary part. What we're going to do here, we're going to try to set up some joints because as you can see, there are no joints created. So we could go and manually define joints. So we can go and assign maybe revolute joint to this guy in relationship to the block. We're going to maybe add an additional joint like translation and joint applicable to piston that moves along that block, and so on. We could continue with this, but I would like to show you the most efficient way of doing this. We talked about this, that motion, as any other application, any other environment, is very tightly integrated within SolidEdge. So let's get rid of this and go back to our assembly environment. In assembly environment, I'm going to explore our relationships. So if I go into Assembly Relationship Manager, which is a really efficient tool for interrogation of different relationships within assembly, we can see that a lot of these relationships are suppressed. So what I can do, I can select all of them and unsuppress in one single operation. Very efficient, very user-friendly. So now to illustrate the tightest integration with motion, if I go back to motion environment, immediately the system senses that there are some assembly relationships that were enabled or exist, and they automatically added to our constraints, in this particular case, joints. So you can see it added axial alignments, revolute 2, and all this information was added automatically. So let's go and modify this study slightly. We want to change the direction of gravity force, and we're going to take a look while we're here. Maybe we want to take change the simulation parameters, and we're pretty much done. So based on the gravity, we can just animate our design, and you can see it moves now in the way that it's supposed to move under gravity. But we're going to go further, and we're going to apply actually some forces and additional parameters. In this case, I'm going to apply, it easily can be done in properties. Instead of free type of motion, we're going to apply velocity. And finally, we're going to add force that will act on that cylinder. Conveniently, we can add force, and we can apply that to the top of the piston. You have to be careful. You want to make sure that it points in the right direction, in this case down. so we can conveniently switch the direction. And also, since we're going to be using this to extract some information for our FEA analysis, we want to define the force value. So in this case, 1150 newtons, that's average force that acts on a single cylinder in a mid-size car. Okay, let's go and animate our study. As you can see, now it acts as it's supposed to be under the force and with the additional constraints. I would like to add a couple more parameters. So in this case, we want to create, let's get out of here, and want to create some relationships for this revolute. We want to make sure that we want to add some faces that are going to be responsible for transferring that load from the piston onto the crankshaft. Let me hide one component. So maybe we want to hide the crankshaft first, and we're going to add the face, which is going to be cylindrical face, as you can see. So we're adding parameters that will help us extract correct information. And then we're going to show the conrod, hide the conrod. For the second face, we're going to select that cylindrical face on the crankshaft. Okay, now that we've done that, we can go and animate this. You can see how easily I was able to define joints based on relationship in assembly, thanks to Titus integration. And now, under the solid edge simulation, we have this crankshaft part. We can transfer that reaction force into solid edge simulation and get more accurate results. So let's see how it happens. But before I do that, of course, we need to see in which position we experience the highest stress. For this revolute, we can go and plot, let's say, a reaction force in y direction, and we can plot reaction force in x direction. These graphs are dynamic graphs, so they show us the most critical position in which the system experiences the highest stress. And you can see that in y direction, the highest stress would be here. We can conveniently click on that graph and position our system in the highest point where force is about 1,254 newtons. And in this position, we're going to go and add reaction forces to our solid edge simulation study. System constantly is watching over our shoulder, so we need to add a couple more elements, and we're going to add these two faces. And after that, we can transfer all these reaction forces into solid edge simulation. So we can see how many loads were transferred automatically, that we could never come up with this type of loads. We have torque, we have couple forces, two torques, gravity. We wouldn't be able to apply all this manually. So motion environment allow us to actually extract this information automatically from a motion environment and apply these reaction forces before we actually process our study. So what's left to do, just go mesh and solve. And we'll get all this information based on much more accurate extracted information from a motion environment. So let's go animate this so you can see how this crankshaft is reacting based on the information that we extracted from a motion environment. So you can see how additional functionality within solid edge portfolio, solid edge assembly environment, helps us arrive at much more accurate and reliable results because we were able to extract this information from motion and bring this into loads for solid edge static analysis.